Thank you very much to the organizers for the invitation and the occasion to speak here. I will present some joint work with Noam Greenberg, Dan Turetsky, and Miroslav Zeleny. All of us are here together for the first time together. The motivation for this work goes back to the Turetsky-Todorchevich G0 dichotomy. It goes back to the beginning of the study of definable coloring. So it gives a characterization of when an analytic relation has a countable Borel coloring. So for me, relation just means binary relation. So there is a Borel relation G0 on the counter space, such that for any Polish space X and any analytic relation B on X, then you have the following dichotomy. Either there is a countable Borel coloring of B, so it's a map from X into omega, which is Borel, and such that the square map of C sends B in the difference. So two vertices that are related should not have the same color. Right? And if you don't have this, you can find a continuous homomorphism from G0 into B. So this is a continuous map from the counter space into X, such that the square map again sends G0 into B. So shortly after that, I proved the consequence of this, characterizing when two disjoint analytic sets can be separated by a countable union of Borel rectangles, or equivalently what we call a potentially open set. So this time you have two Polish spaces. A and B are disjoint analytic subsets of the product, and you have the following dichotomy. Either you can separate A from B by a countable union of Borel rectangles, or you can find two continuous maps from the counter space into X0, X1 respectively, such that the product maps F times G sends G0 into B again, but also the diagonal of the counter space, so the set of alpha, alpha for alpha in the counter space into A. So conversely, it's also possible to recover the G0 dichotomy from this corollary. So these two results are equivalent, which means that the properties of having a countable Borel coloring or of the possibilities to separate by a countable union of Borel sets are extremely related properties. It's a set of unions of Cn times Dn, and Cn and Dn are Borel. Okay, so after that, in our first paper with Miroslav, we studied the existence of a level-by-level version of these two results. And for colorings, we could do it for the first three levels. Again, if you fix an ordinal 1, 2, or 3, and you can find a zero-dimensional Polish space xi and the Borel relation gxi on xi, so that for any Polish space, and you have to assume that it's zero-dimensional if xi equals 1, but not after. And again, if you take any analytic relation beyond x, then you have the same dichotomy, but instead of having Borel colorings, you have delta 0 xi measurable colorings. So delta 0 xi measurable means the preimage of any open set is delta 0 xi. But apart from that, it's exactly the same dichotomy. And the main question is, can we generalize this? And the point of this talk is to present a new light on the case of three colorings, because in the case of three colorings, both are proof and the minimum objects were very technical with a lot of complicated combinatorics, so extremely hard to generalize. And the point is to present a new approach with more chances of generalization. That's what I do want to do in this talk. So we need to forget about some of these combinatorics. We need something more abstract to have a chance to generalize. So what about rectangles? We could do that for the first two levels. And again, it's similar. You have two zero-dimensional polyspaces and disjoint Borel subset of the product. So that, as before, if you take two polyspaces and two disjoint analytic subsets, you have the corresponding dichotomy, but instead of having countable unions of Borel rectangles, we have countable unions of sigma zero psi rectangles. Apart from that, it's the exact same dichotomy. And again, what about the generalization? So I will mostly talk about three colorings. But one last thing maybe about the general case, we have topological characterizations in general. So we know exactly when there is a delta zero psi measurable coloring or when you have the possibility to separate, like this. And the tool for that is some effective topologies that were introduced by Yann Louveau for some other purpose. So assume that X is recursively presented. T1 is just the topology of X. And if psi is at least 2 and less than omega 1 ck, so psi is a topology generated by the sets which are both light-phase sigma 1, 1 and bold-phase pi 0 less than psi. So I start with rectangles. So if you take any recursive psi, and again, recursively presented polyspaces and disjoint light-phase sigma 1, 1 subset of the product, then you can separate by a countable union of sigma 0 psi rectangles exactly when A does not meet the closure of B for the product topology psi times psi. And as a corollary of this, we have the same for coloring. So again, we want to avoid this zero-dimensionality problem. So assume that this time psi is at least 2. So X is a recursively presented polyspace, and B is a light-phase sigma 1, 1 relation on X. Then you have a delta zero psi measurable coloring countable of B exactly when the diagonal of X does not meet the closure of B for the same product topology psi times psi. So I did wanted to insist on that because we have this product topology psi times psi. What does it mean? It means it's a quite strong evidence that to solve these two problems, we will have to work with projections because we have product topologies. And this will be an important remark in the sequel. So this is why I wanted to say that. So now I'm going to present the more abstract approach. And it's, in fact, the representation theorem for Borel sets that is due to Gabriel Debs and Saint Raymond. So what is the origin of that? It's this classical Luzin-Suslin theorem saying that any Borel set in a Polish space can be seen as a bijective continuous image of a closed subset of the Baire space. Turetsky proved a level-by-level version of this. Namely, if B is pi 0 psi, then the inverse bijection of F can be sigma 0 psi measurable. And the representation theorem of Borel sets is a refinement of this Turetsky result. So, in this representation machinery, we identify an element alpha of the counter space with the sequence of all its initial segments that I call H of alpha here. And the point of a representation is to extract good subsequences of this sequence of initial segments. So let me go to the details. It's based on the notion of a tree relation. So a tree relation, I will consider they live on the set of finite binary sequences. And a tree relation is a partial order on this set. which has a minimum element, which is the empty sequence, and such that the set of predecessors of any sequence is finite and linearly ordered by the relation. So this is what is a tree relation. So typically, the extension is a tree relation. The number of strict predecessors of S will be important, denoted by HR of S. The notion of R branch is very important. What is an R branch? It's a maximal subset for the inclusion, linearly ordered by R. And those that would be very important for us are the infinite ones. So we take a notation for this. The set of infinite R branches is denoted by R square bracket. Then we put some topology. This set square bracket R is a subset of this set. So 2 to the less than omega to omega. So we take the product of the discrete topology. And since it's a closed set, it's a nice Polish space. The basic Lecomte sets are called an NRS. These are the sets, the elements in the square bracket R in which S appears. And if S appears, it has to appear precisely at this position, HR of S. So now we consider two tree relations with an inclusion like this. R is contained in S. And there is what we call a canonical map from square bracket R into square bracket S. So you simply associate to an element of a square bracket R the unique S branch which contains it. It is, with the topology we consider, this is always continuous. Now we come to the crucial notion of this machinery, which is the notion of distinguishedness. So again, you have this inclusion of R in S, and you say that R is distinguished in S is if you have two finite sequences S, T, U in this order for the big relation S, and if S is R related with U, so the shorter one is R related with the longest one, then it has also to be R related with an intermediate one. So in other words, if you like, if S is good for U, it's also good for S, for T. So this is a crucial notion in this representation thing. This is an algebraic property that is very important. And then what we do is we iterate this. So we take a countable ordinal and take a family indexed by eta plus 1. We call this a resolution family. If at successor steps you have distinguishedness, and if at limit steps you have intersection. Now we are able to state the representation theorem. So I will state it only for limit ordinals, for successor ordinals. There is also a version for limit ordinals, but it requires some uniformity, and then I don't want to get into this. Because we will mostly be interested in the case where eta with this eta equals 2. But. So eta is a countable ordinal again, and P is a Pi0 eta plus 1 subset of square brackets extension. Then you can find a resolution family as above. That the big relation is the extension relation. The canonical map from the square bracket of the smallest one into the square brackets of the biggest one is a continuous always, but it's a bijection, and whose inverse is a sigma 0 eta plus 1 measurable. So we have something like in the Kuratowski result, right? And also like in the Luzin-Suslin result, P becomes closed if you see it inside square bracket R eta. So this is a refinement of Luzin-Suslin and Kuratowski. Well, this theorem has a number of applications. I don't want to insist on that. It's just here to say that as long as Borel classes or even wedge classes of Borel sets are involved, then the representation theorem is a powerful tool. Maybe I will say a few words about the last one because it's close to the rectangle problem we have. For the countable union of sigma zero psi rectangles, Alain suggested to me that to solve this problem, it could be interesting to desymmetrize the problem. So I thought about this, and I could do it in this way. So if, for instance, the left side of the rectangle is always open, then it works. Of course, you can reverse left and right. But, okay. So, yeah. So it's an indication. This gave me the conviction that to solve these two problems, we have to find the right way to apply the representation theorem. Okay, so now I come to strong representation, because in fact, we have a clue, but it's more than representation, it's strong representation. So take, again, a countable ordinal, and this time P is not pi0 eta plus 1, it's pi0 eta plus 2 for some reason. And I will say that P is represented, as you can guess, if we can find a resolution family exactly as before. And if you have this, you can define two objects that will be very important. First, this set D. So what does it mean? It means that it's the set of finite sequences that appear in the representation of a guy in P. Essentially, this is exactly the meaning when P is not empty. And if P is empty, then you add the empty sequence. But intuitively, the meaning of that is that S is part of the representation of a guy in P. And if you have a non-empty finite sequence and an ordinal, which is at most eta, then it will be useful to consider the row predecessor of S. So this is the longest proper initial segment of S, which is our row related to S. So this is well defined because you can always take L equals 0. The empty sequence is related to anybody. So this is well defined. So what happens here? It means that we have different predecessors for S. It means that we have different levels of past. Remember, we have to work with projections. So in order to construct our continuous homomorphism, we will perform a counter-like construction. And in counter-like constructions, we made finite approximations of our infinitary objects, right? And in this kind of results, we have to consider these different levels of past. Okay, but we are on a product, so we have two sides. And, okay, assume that on one of the two sides, we can well remember what happened on one side. Usually, we have to go back to the oldest predecessor. And maybe we can remember what happens for all the different predecessors. But when we arrive at the oldest predecessor, what happens? Well, we work in a projection, so it's in the projection. So what can you do with a projection? Take a witness for being in the projection. But what happens on the other side? We are far away in the past. And if we are far away in the past, we are completely unable to remember anything that happened between the recent past and the oldest past. And this, where we are in trouble if we cannot fix this problem. So the heart of the matter of these two problems is to solve this problem. So is to say, okay, maybe on one side I can remember everything, but on the other side, then the most recent past has to coincide with the oldest past. This is the key idea. And the good news is that for 3 colorings, at least, it's possible. So this leads to this extra condition that gives strong representation. Again, P is strongly represented if we can find a resolution family as before, with an extra condition, which precisely talks about the difference between the most recent past and the oldest past. So if these two coincide, we have no problem. But if they are different, we have to say something. So there is a first part, say that S cannot be in D, and so it cannot be part of the representation of a guy in P. And the second part is more technical, but it's very important. So if the most recent past is different, then we have at least one U in between. Assume that U and V are in between S and the eta predecessor. Then there is a T which is in D, and which is strictly after the eta predecessor, and which is R eta with U and V. And there is a last condition that is for free when eta equals 1, and we will focus on this case. We need that the eta predecessor is R eta with T, but if eta equals 1, it's for free because R1 is distinguished in R0. But I write it like this because it allows a generalization. But, okay. So this is an ad hoc condition that comes from the proof, and this is quite technical, so it needs motivation. So in order to motivate this definition, I will sketch the proof in the new approach. So I need to construct X3 and G3, so the space and the digraph. So we start with an arbitrary Pi03 set of the counter space, Q3. And this map H, remember, it associates to any element of the counter space the sequence of all its initial segments. With the topologies, we consider it's a homomorphism. And so H of Q3 is also Pi03, and we call it P. So we assume that we have strong representation. At the moment, we don't know if it's possible, but it is. And if you have strong representation, you can define D, the set of finite sequences appearing in the representation of somebody in P. And we have canonical maps, so the one I defined. But there is also another one, which is an intermediate one. If you replace R square bracket R2 by square bracket R1, you have another canonical map, which would be very useful. We need to define notions of predecessors, of one predecessors for finite or infinite sequences. So for infinite sequences, we say that S is a one predecessor of alpha. This writing means that S is part of the one representation of alpha. And if it's easier to understand at finite levels, it just means that S is R1 with T and different from T. But this is what it means essentially at infinite levels also. And we need a map, which is a coding map that for the moment is completely arbitrary. So it's defined on D and takes values on finite sequences. So Q3 is arbitrary, mu is arbitrary, and the resolution family is arbitrary, but it's strong. So it's quite general. Now we're ready to define the good space, X3, and it is in 2 dimensions, in fact. It's made, the elements of X3 are elements of the counter space, such that for any LM, if the corresponding initial segments of alpha are one predecessors of alpha, and in this order, so M is smaller than L, And if these two initial segments are in D, then the longest one, alpha restricted to L, codes with the help of this map mu, the initial segment of the second coordinate alpha given by the smallest one, m. So it's not m, it's m plus 1, and this plus 1 is important. The important coordinate here on the gamma side is the last one, it's gamma of m. So what is important is that alpha restricted to L codes gamma of m with the help of this map mu. Okay, now we need to define the digraph G3. So a bit more of notation. If you take alpha out of Q3, then you can find an alpha maximal such that in the one representation of alpha, you are in D. There is a last in D in the one representation of alpha. And what is important is the length of this initial segment of alpha, and we call it C alpha. Now we are ready to define the digraph. It's a bit like G0. The two coordinates differ only at one coordinate. The first is the same, and the second differ only at one coordinate. And the position, first, alpha is out of Q3, and the length of this S, so the position at which we have a different coordinate, is exactly C alpha. Good. So now we have the space, we have the digraph. So we will focus on the one-holds part of the theorem. You know, we are looking for a dichotomy. So there is the one-holds part and the exactly one-holds part. I will not speak about the exactly part, I won't have time for this, but I will focus on the one-holds part. So it's the exact same statement as before, so I don't insist. So I want to sketch this just to motivate strong representation. Without loss of generality, we may assume that X is recursively presented, as usual, to simplify notation, and B is light phase sigma 1, 1. Coming from this topological characterization, we can define the following set. It's the union of the T2 open sets, which are covered by countably many G delta sets whose square does not meet the relation B. And this sequence of G delta sets is uniformly delta 1, 1. So if U is everything, then we have a coloring. So without loss of generality, we may assume that U is not everything. So call Y the complement of U. And of course, it has to be non-empty. And one can check that it's a light phase sigma 1, 1 set. And the crucial property of this Y is this following claim. If you take a T2 open set, which meets Y, then the square of the intersection has to meet this relation B. We say that this intersection is not B discrete. So now, okay, we want to perform this counter-like construction, so we made finite approximation of our continuous homomorphism. So we simply copy the definition of the space at finite levels. So this gives this. So we define a set of pairs, and the elements of this set, I will call them pairs in the future. Our pair RP SP. The length of SP is one more than the length of RP, and then you copy the definition. This time L and M are at most the length of RP, and then you take the exact same condition as in the space. We need a few notation. So we had this C at this infinite level, now at the finite level. So if you take pairs P and Q, so here I will first talk about P. So the length of P is just the length of RP, and CP is the longest natural number, which is at most the length of P, such that the initial segment of RP of length L is R1 related with Rp, and it's in D. If you have one pair, you can define a dual pair by simply, you keep the same R, and you change the S at only one coordinate, which is exactly Cp. And the epsilon of P is just the value of Sp at this position Cp. So we define some predecessors for finite sequences, but we can also define similarly predecessors for pairs. So you say that Q is a zero predecessor of P if you have zero predecessors for both R and S. It's a one predecessor if it's a zero predecessor, and if on the R side, on the left side, you have R1 relation. And the natural thing for strict extension is extension and difference. Last thing, if Rp is non-empty, we had the notion of predecessor for finite sequences, but we also have notions of predecessor for pairs. And this is the natural definition. It's the row predecessor of P is the longest pair, which is strictly row before P. So now we are ready to state the condition, essentially, of the construction. So remember, we had this tick-sided topologies, but we also need some other effective topology, which is the Gandy-Harrington topology on the product X squared, which is defined by the light for sigma 1,1 set. And it's known that it's zero-dimensional and Polish on the dense basic open set that I will call omega. We don't really need to know what it is, but this one works. You can take the Z in the product for which omega 1Z is omega 1ck. So we construct for any pair P three different objects. We construct a point in Y, xp. We construct an effectively open neighborhood, capital XP of XP. And we will construct sigma 1,1 subsets of the product called UP, satisfying the following condition. Well, the first condition is witness for non-emptiness. So I already mentioned the first part. And the second part, say that XP hat is in UP, or vice versa, depending on epsilon. So to ensure continuity of the homomorphism, we say that if Q is a proper zero predecessor of P, then the closure of XP has to be contained in XQ. UP will always be the same as UP hat. And it will be a subset of B intersected with Y2, which is non-empty by definition, by what we did before. And if it's non-empty, it has to meet omega, which is dense. So, and then we need also inclusion into this product of open neighborhoods in the right order. We need vanishing diameters. This is a usual condition. Okay. And sometimes we need to decrease also in the sigma 1,1 sets. When will it be possible? It will be possible when we have a one extension for which almost all the the pairs between Q and P are out of D, except maybe Q. But the last condition is not useful to prove that the conditions imply the theorem, but they are useful to prove that the construction is possible. This is a deep condition saying that it relates the one relation with the closure for the one topology, for the projection, so the right projection, the projections corresponding to Q and P respectively. So one can check that if we have this, then we have the part two of the dichotomy. And this construction is made by induction on the length of pairs. And we always consider simultaneously P and P hat. So the first case is easy, is when the length of P is 0. So we simply take the effectively open sets to be everything, and to UP and UP hat is what I explained before, which is non-empty, but because of what I've said before. This is the density of omega. This is an easy case. So the first difficult case is when the length of P is non-zero and RP is in D. We start to apply strong representation. The first part of strong representation tells you exactly this. The zero predecessor of RP is the same as the one predecessor of RP. This implies that all the zero predecessor and the one predecessors of P, P hat, and all together are the same. And this is what allows us to do this case. Once you have this, you just apply the induction assumption. So it says that, okay, the inclusion conditions that we have to ensure in the construction are all transitive. So it means that it's enough to ensure them for the immediate predecessors. So the immediate zero predecessor of P, so X index this, is in this intersection by induction assumption. But the first part of the intersection is a T2 open set. So we can apply the claim. The claim gives you 2 points in V, XP and XP hat, such that the pair is in B intersect omega. We have to take the right side depending on epsilon, but okay. And then once you have this, it's done. You just have to take small enough neighborhoods. And because of these conditions in red, we have no problem. So 2 more cases. Case 3 is another easy case. This time RP is not in D, and it says that on both sides, the recent past is the same as the oldest past. In that case, you can just copy the point and shrink the neighborhoods, and it works. So this is another easy case. And the last case is when this does not happen. So we know that now RP is not in D. But the path is not the same on at least one of the 2 sides. So assume, for example, that it's on the left side, that the 2 levels of path are different. And the point is that on the right part, it's the same path. And this is the second part of strong representation. So argue by contradiction to see that as P is strongly represented, and also because between RP and RP minus 1, you have the RP minus 0 and RP hat minus 0. So you can apply the second part of strong representation. It gives you a T in D, which is strictly after RP minus 1, and which is R1 with these 2 guys at the 0 level. We know that P minus 0 is a pair, and we know that T is R1 with RP minus 0, and this implies that this thing is also a pair. But we know that P minus 0 is a pair before P. So in particular, SP minus 0 has to be an initial segment of SP, which implies that here you can replace SP minus 0 with SP. So this is on the left side, and you can do the same on the other side. And now, one last remark. RP restricted to CP, remember, it's the last guy before RP, which is R1 related with RP and which is in D. It's the same as this, RP minus 1 restricted to CP minus 1. And so it has to be R1 related with RP minus 1, but as I noticed, this condition is in blue, that is for free. Here, for eta equals 1. This is a proper 1 predecessor of T. So mu of T has to extend this sequence. SP restricted to length of T plus 1. In particular, SP of CP is exactly mu of T of CP. And you can do the exact same on the other side, because CP and CP hat is the same. But this is contradiction, because these two things differ exactly at this position CP. So now we're essentially done. We take again this induction assumption, it's the same as before, and we remove the closure, so we take an XP in the intersection, and then we take a witness. And because on this other side, the recent past is the same as the old past, we have no problem. So we just choose small enough neighborhoods to finish the proof. Okay, so this is the one-holds part of the theorem. I have no time for the exactly part, so I will skip this. We construct a Pi03 set, which is a bit special, not so special, but a bit special. We construct a particular strong representation. And we construct a special map mu, coding map mu. And then we have the full dichotomy. Okay, it's the same as before, so I don't insist on that. Okay, one last word. So we have this strong condition, the strong representation. So it's an ad hoc definition, which is quite technical. So it looks very particular, but in fact it's not. It's completely general at this level 3. So the last result I want to state is that if you take any Pi03 set, then it is strongly represented. And maybe 1 minute just to give you the objects without any proof. But how is it constructed? So you start with an arbitrary representation, which exists by the Debs and Saint Raymond theorem, and we define a map from finite sequences to natural numbers. Start with a 0, and by induction on the length of S, you say that n of S is n of the 0 predecessor plus 1 if S is in D, and n of the 1 predecessor if S is not in D. And once you have this n, you can start to construct your resolution family. So you start with the extension. You have to do this. And what about S1? Well, S and U are S1 related if they are S0 related, and anything in between S and U has an n, which is at least the n of S. Finally, we have to construct S2. What is S2? S and U are S2 related if they are S1 related, and if either S is in D or anything in between S and U with an S1 relation is out of D. And the thing is that this gives you a resolution family, which is a witness for strong representation. So any Pi03 set is strongly represented. So thank you very much for your attention.